So we're going to get started. So let's kind of see exactly where we are. And I would suggest anytime that you're sitting down to work your physics problems, you might want to start developing your own cheat sheet. And things that you would like to include on your cheat sheet are like as follows. We've got our V final squared is equal to V initial squared plus 2 times my acceleration times my change in position. I have my change in position is equal to V naught times T plus 1/2 acceleration times time squared. And then I have V final is equal to V initial plus my acceleration times time. Then you probably want to start making sure you have your triangle so that you've got your triangle for reference information. So here's our angle. Here's the hypotenuse. Here's the opposite side. Here's my adjacent side. And then I can write my cosine of my angle is equal to the adjacent divided by the hypotenuse. The sine of the angle is equal to the opposite divided by the hypotenuse. And the tangent of the angle is equal to my opposite over adjacent. So you've got your toolkit ready to go and you can play with it. So far in the videos, so far in everything that we've done, we've looked at one-dimensional motion. So that's looking like going left and right, or up and down. Or if I'm on an inclined plane, I can still do one-dimensional motion. I'm just reorienting my frame of reference such that I'm moving in one dimension. I can look at it as being along this plane, and I can judge it as one dimension. Now we can rewrite these for the cases, so we can rewrite them as special cases. For when we're dealing with gravity, and we use our change in position, either our change in X or our change in Y as equal to height. And we can rewrite these as our V final squared is equal to V initial squared plus 2 minus G H. We can do my height is equal to V naught T minus 1/2 gravity times time squared. And then I can do V final is equal to V initial minus GT. And this is in reference for when I'm traveling up and down. And I can rewrite those into a variety of different ways. And you can see it in your special cases, and you can look at how this is going forward. So that's your cheat sheet. And I would encourage you as we start moving through things to kind of keep your own cheat sheet ready to go. If you were in an in-person class and I could actually say, all right, we're going to take an test in person, I would usually say you can bring your own cheat sheet, because the act of building this cheat sheet really is a way of helping you study and understanding where each of these equations are coming from and how those are going to be better used. So what we're getting ready to do, and let's think of this situation. So I'm on a train. Okay, I'm on a train And I actually have a couple of videos in those example videos, and I'm a person on the train. And I toss my ball up and my ball comes back down, whether my train is standing still or my train is moving along. I have this situation where if I'm sitting on the train and I'm sitting at my desk, or I'm on the airplane, even think about it from an airplane point of view, and I'm bouncing a ball in my hand, the ball is just going to act like it's going up and down. It doesn't matter whether I'm sitting in the car and I'm moving, the ball is going up and down. And this is where we get this idea of independent motion. What's happening in the X direction is independent of what's happening in the Y direction. And you saw that in the basketball toss. In the lab that you turned in on Sunday, you saw that in the basketball toss, because if I looked at a position versus time graph, for the Y direction, the basketball did this. My basketball followed that kind of a curve, and you actually got that data, and you showed that the data actually did that. But if I looked at it in the X direction, and this was in the X direction, you actually saw this. Position got further away as we moved across the page. So we actually saw two different behaviors in the X direction and the Y direction, and they were independent of what was going on. Now, in this case, when we think about the guy tossing the ball, he's throwing the ball up and he's tossing it. This one had an acceleration. And the acceleration was gravity. Gravity affected this situation. This one didn't. And when we get to forces, we're going to hear the term an object in motion remains in motion unless acted upon by another force. This one had no acceleration. So in this case, my X position was equal to the constant velocity, because there was nothing there to change my velocity, times time, and the slope of this line was going to equal my constant velocity. Now this one we could write our equation of our curve here, which you guys got. This would say 0 is equal to some value A times time squared plus some value B times time plus some value C. So that's the equation of this line that I got. So let's look at that for a second. One of our equations of motion was my change in my y position is equal to my initial velocity times time plus 1/2 my acceleration times time squared. I'm going to put that in the same, I'm going to put that in the same form as what I just wrote down here. So I'm going to put that in the same form. So I'm going to have 0 is equal to 1/2 my acceleration times time squared plus my initial velocity times time minus my change in position. And if I look at my equation for my line, and I'm going to go ahead and make this a g because we know that's an acceleration due to gravity. And that's going to make this make a little bit more sense. And we don't have two a's that we're having to deal with. What this says is that my a is going to equal 1/2 of my acceleration due to gravity. My b for that equation is my initial velocity. And my c is going to be the negative change in y. So we can use this model to actually read these values. And that's what you did. This is what you did for the planetary data graphs. You either did that or you did this. My velocity finals equal to my velocity initial plus my acceleration times time. And that was going to be, we're going to make it a little easier. I'm going to get my velocity finals equal my initial velocity plus or minus, we're going to go ahead and use a minus my acceleration due to gravity. So I could do it that way. And so now if I did this as 0 is equal to negative gt plus v naught minus v final. That's my change in velocity. And if I have that, my slope of my line, or I can do this as y is equal to mx plus v. I can do this as v final is equal to my y variable. My acceleration or my g is equal to the slope. And my b is equal to my initial velocity. So we can read actual scientific information from our graph. And we showed with our basketball graph that we have independent motion. Now, at some point last week, we talked about this idea of describing something in space. And if I used my Cartesian coordinates, and we picked out this point, I could say this is a vector that's describing this point. And we said, hey, we could add vectors head to tail. We just kind of mentioned it. I could add my vectors head to tail to get this. And we could represent this as an x, y. Or we could use, this is my Cartesian coordinates, or we could use a polar coordinate system. And this was r, and this was theta, and I could use an r theta. And then I could use my trigonometry, my triangle, to describe that position. All right. So first thing is, let's kind of describe a couple of things. So we're going to be little kids, and we're going to do a lovely city here. Let me give myself a representation. All right. So this is my start spot. And this is my stop. Now, we've said vectors have direction and magnitude. So my vectors have direction and magnitude. Well, I can go 4 blocks this way, and I can go 4 blocks this way, and I can get my position vector now. This is my position vector. Looks like this. Basically, what we've done is we've added 2 vectors head to tail. Now I can get to this spot a couple of different ways. So I can go ahead and do this first. And my green one here. And I end up at the same stopping point. So it doesn't matter which order I use it. And then if you go back to your algebra, that's the communicative bit. So what this is we call this vector A, and we call this vector B. What I've just shown is that A plus B is equal to B plus A. I don't have to worry about the order. It doesn't matter. I don't have to worry about the order. Now, there are lots of other paths that I can use to get there. So I'm going to mathematically represent vector A as, in this case, we're using 4, and my units are blocks. Vector A is 4J. That is a way that we can represent going in the y direction. So what we say, this little j with the caret is a unit vector, meaning the magnitude is 1. And the direction is in the positive y direction. On my vector B, this so happens we have that same magnitude, 4, and we're going to use an I, where I is a unit vector. So it has the magnitude of 1. And this is in the positive x direction. So my vector A plus B, I can only add the y's together, and I can only add the x's together. So my vector A plus B is going to equal 4i plus 4j. So I can that's what this vector is 4i and 4j. So we can break this one vector that's in this awkward diagonal into its component parts in its x and y parts. So I could do it or something really weird. So let's do this. I'm going to start with vector. I'm going to start a vector like this. So I'm going to do this vector. And I'm going to call that vector C. Then I'm going to do this vector. I'm going to call that vector D. And then I'm going to do this vector, and I'm going to call that vector E. So we're going to write vector C. Vector C, based off of our picture, is 2, 2. So it's 2 in the I direction plus 2 in the J direction. Vector D was 2 in the J direction. And vector E was 2 in the I direction. And I'm going to do C plus D plus E. I'm going to add my X components. I'm going to add my X components, so that's 4I. I'm going to add my J components, and that's 4J. And I'm back at this long vector piece. Now, if I want to subtract a vector, so I can do a negative, so we'll use C, we're going to use this, we'll call this vector V. So I'm going to have vector V, which is equal to 4I plus 4J. And I'm going to subtract vector C. And that's going to be a minus in front of my 2. That's going to be a minus, and I'm going to go ahead and do a minus in front of my 2J, because I can do that negative there. And so now B minus C is going to be 2I plus 2J. So what I've done here is my vector V, there was my vector V. And now I've subtracted off one vector C. And this gives me my resultant vector that I'm left with. I can do 2 vector C is going to equal 2 times my 2I plus 2 times my 2J. So 2 times vector C is going to be 4I plus 4J. So I can utilize this. So a lot of this algebra, or this vector algebra, is in Appendix A. And it's in your chapter. And it's starting at chapter 3. So this is starting into chapter 3, that 2-dimensional motion. And the reason we do all of that is because I'm going to shoot an arrow. So this is an arrow. And I'm going to tell you that it has a velocity of magnitude 3 meters per second. And we're going to set it off at an angle of 30 degrees. And we want to get at that. We want to get to the independent motion. So this vector has a y component. And it has an x component. And how do we get those x and y components? This is where our trigonometry comes in. That y component is going to equal the velocity in the y direction which in this case is going to be our 3 meters per second times the sine of my 30 degrees. Because this is the opposite side, opposite over my hypotenuse. My hypotenuse is 3. Is going to give me my angle. So my sine of my 30 degrees is going to equal the y component of velocity divided by the overall magnitude of the velocity. So I can actually get its y component. The x component, I'm going to do the same thing, except now it's the velocity in the x direction. So I'm going to use cosine of 30 degrees is going to equal the velocity in the x direction divided by the overall magnitude there. So I get my overall magnitude cosine 30 degrees is going to give me the velocity in the x direction. And so now I'm going to get 3 meters per second cosine 30 degrees is the velocity in the x direction. So now we've got these things taken care of. We've got them in their 2 components. We can actually calculate those numbers. So it's 3 times the sine of 30. And this is 1.5 meters per second. 3 times the cosine. 3 times the cosine of 30. And that gives me 2.60 meters per second. And that gives me the velocity in the x direction. But what this is going to do for us is it's going to allow us to take problems apart. And we're going to be able to look at our velocities in their individual parts. Okay? And so we can calculate these components. And then we can start looking at the behavior. And that's what's going to get us into what we call projectile motion. But let's do something real quick, and let's do it this way. So I've got an airplane. And it's flying at, we're going to say 100 meters per second in the x direction. And we're going to drop a package. And if I do that, it's going to go like this. This is the fall. That's the fall. Now, this is the time is equal to 0 when we drop the package. But this is the time when it lands. And we know, because we've done it before, we've seen it before, there's a distance that is traveled from that spot. So we're going to say, we know how high we're flying. We're going to say we are at 500 meters above the surface. We want to know how far away the package lands away from the plane. So there's things that we know. Okay, there's things that we know. We know the initial velocity in the x direction is equal to 100 meters per second. We know our change in our y is, and we're gonna say this is down and that's a negative. So my change in y is a negative 500 meters. We also know our initial velocity in the y direction, and in this case it's 0 because we didn't throw it down, we just dropped it. And what we want to know is this distance. All right, couple of things. So let's look at our equations of motion. So we're going to take out our toolkit. There's our toolkit. And we're going to look at what's happening in the x direction. In the x direction, the acceleration is equal to 0. There's nothing, once it leaves the plane, there's no acceleration. So my change in position is equal to the initial velocity in the x direction times time. Or in this case, writing it for the equation that we're dealing with, we have that right there. And that's the only equation that we have for the x direction. For the y direction, I got a couple of things. Y direction, I have my change in y is equal to my initial velocity in the y direction times time minus 1/2 gravity times time squared. I have my final velocity in the y direction is going to equal my initial velocity in the y direction minus 2g d, but that d is negative, so that's going to be positive. And I have my final velocity is equal to my initial velocity in the y direction minus gt. So those are my equations in the y direction. Well, I have two unknowns. I don't know time, and I need time in order to solve for this. So since I know I have a change in y, I'm going to use this equation here. So my negative 500 meters is equal to my initial velocity in the y direction times time, except my initial velocity in the y direction is 0, so that equals 0, minus the acceleration due to gravity divided by 2 times time squared. I'm going to solve for time. So I'm going to get 1,000 divided by gravity, and that's meters. Meters per second squared is equal to t squared. T is going to equal the square root of 1,000 divided by 9.81. And I've got a second squared under there, so I'm in seconds. So my unit analysis says I've done this right. So I get 1,000 divided by 9.81. Now I gotta take square root. And it says it's gonna take 10.1 seconds for it to fall 500 meters. And that's negating air resistance and all that good stuff. So now I've got that. Well, my distance now is going to equal my 100 meters per second times my 10.1 seconds. And that's going to be 1,010 meters or 1.01 kilometers. So that's why we have to make adjustments when we're dealing with bombing runs, dropping survival packages, all of those things. We have to account for how long it takes it to fall, because it's going to fall in that projected arc. We're going to get that projected arc to have it fall. And I have to take my coordinates in separate components. I've got to do separate components. So let's do this again, because we kind of want to look at it again, because we're going to be doing the laboratory experiment where I'm going to drop a ball. And what you're going to get in your data when you do your ball drop is my initial velocity is equal to 0. We don't have a good way to do our final velocity, but one of the things we can measure is the time that it takes to fall. And we can measure the height. So what's going to happen here is I'm going to use I'm going to use this one. I'm going to use V final squared is equal to, is that the one I'm going to use? Nope. I'm going to use the change in Y is equal to minus 1/2 GT squared. I'm measuring gravity now. I know my height. I know my time. And I want to caution you about this time. When you do your experiment that we're going to talk about tomorrow, you want to make sure that whatever time value you're getting makes sense. And that'll become a little clearer when we talk about the experiment. So now I've got minus H is equal to minus G over 2 times time squared. So I've got that cancels out. I get 2H divided by T squared is equal to my acceleration due to gravity. Let's double check to make sure my units make sense. I'm going to be in meters per second squared. Gravity is in meters per second squared. So my dimensional analysis makes sense. So I can actually measure my acceleration due to gravity by measuring the time that it takes to fall. You can also do it in a position versus time plot. So I can do position, and I can do my time. This is going to give you a curve, because I'm going to be, my change in position is equal to my 1/2 my value for A times squared. This value of A, if I do a curve fit, we know is going to be related back to gravity. And you'll be able to deal with that particular piece as well. So you may get a graph that looks like this, or you might get a graph that looks like this, depending on how you do your experiment and how you set up your experiment. But we can read gravity off the graph. We can determine gravity here, but we're going to be measuring the time of fall and our individual positions. And we'll talk more about that tomorrow for your lab. So this gets us back to our lab. But what's happening here is it doesn't matter, because we could drop a ball, we could roll a ball off the table, and you're going to be doing that experiment as well. You're going to roll the ball off the table and get that experiment. We're going to be measuring our gravity, and you'll get this experiment. So you've got those two experiments that are coming. And you can start to see why breaking up our vectors into the individual components makes sense. Because we're going to have to deal with that independent motion. So I'm going to stop there. Stop recording. Open it up for questions.